Hello class, let's do another lesson plan here on polynomial functions. So this is part 2. I did one yesterday. And we're still not going to be completely done with it. I want to do one more. It's a big long section, but it's a fun one. Okay, so again, this is math 1220, polynomial functions continued. So let's start off with this example. Let's consider the polynomial function f of x equals 3x to the fifth minus 3x to the fourth plus 2x squared plus x minus 4. And just two things we want to do here. State its power function and state the end behavior of f. We haven't talked about end behavior yet. So let's do the power function first. Power function, stating it is very straightforward. All you do is you look at the original function, and as long as it's written in standard form, that implies the highest exponent term is written first, that leading term will be the power function. So don't forget to write y equals 3x to the fifth, or f of x equals 3x to the fifth. So that one's done. And now, what is the end behavior of this function? That means as x gets really big, so whenever you want to find the end behavior, immediately that means you write down these two rows. So you have to kind of memorize these two rows. As x goes to infinity, where are those y coordinates going to? And you got to fill in the blank. And then as x goes toward negative infinity, where are those y coordinates going? So that tells you the ends of the graph, what's happening. And the ends of the graph is over 99% of the graph because it goes on toward infinity, both positively and negatively on the x-axis. So let's see what we got here. The end behavior of a polynomial function is described by its power function, and in particular is an even degree power function or odd degree. Isn't 5 an odd number? So this is an odd degree power function. I'm going to write that down. Odd degree power function. I'll write it as PF for power function. So what do we know about odd degree power functions? I talked about this the last video. We know, isn't y equals x cubed an odd degree power function as well? So as if this weren't simple enough to analyze, let's make it even simpler and just call it the power function, say y equals x cubed. Let's just play the game of pretend. Pretend that's the power function, because I'm really interested in, is it an even degree or odd degree power function? And this is an odd degree. So we all know what y equals x cubed looks like. It looks like that. So notice with all odd degree power functions, the ends go in opposite directions through the first and third quadrants. And more specifically, let's answer it formally now, the end behavior. I kind of said it in English, what the end behavior. I talked about the ends of the graph. The ends go in opposite directions through the first and third quadrants. But more specifically, for end behavior, it's nice to write these two rows down and fill in the blanks. So as x goes to infinity, where are those y coordinates going? So let's look at this graph I drew. As x goes to infinity, so along the x-axis, that means we're going this way toward positive infinity. And isn't it only this upper part of the graph which comes into play as x goes toward positive infinity? It's going up forever, but also to the right forever. So notice as x goes toward infinity, what's happening to those y coordinates? Aren't they going up, up, up? Let me draw the y-axis here. This is going toward positive infinity on the y-axis. So, and this is, I should label this axis as the x-axis. And so does that make sense? When we look at this graph, as x approaches infinity, aren't these x coordinates getting bigger and bigger toward infinity? What's happening to these y coordinates? Are they going up toward positive infinity? Like for instance, this ordered pair for that point. Wouldn't that be a big x coordinate and a big y coordinate? So aren't these y coordinates going toward infinity on the y-axis? Yeah. So I'm going to write infinity right there. Okay, we're halfway done with the end behavior. Now let's do the second row. And by convention, the negative infinity is written in the second row. So again, end behavior means as x gets really big, either positively or negatively. So as x goes toward negative infinity, what's happening to those y coordinates? So let's look at our power function y equals x cubed as x goes toward negative infinity. So now we're going this way toward negative infinity. And what's happening to those y coordinates? So as x goes toward negative infinity, isn't it just this part of the graph, the bottom part of the graph, which comes into play? And isn't it going that way? So as x is going toward negative infinity, what's happening to those y coordinates? Aren't they going toward negative infinity on the y-axis? Isn't this, like if I draw a point here, what's the ordered pair of that point? Isn't the x-coordinate going to be like negative 400? I don't know. And maybe the y-coordinate would be, well, I guess it would be negative 400 cubed, which is a negative big number. So can you see how the y-coordinates are going toward negative infinity? As x goes to negative infinity, the y-coordinates are going toward negative infinity. So I'm going to put negative infinity right here. And that's done now with the end behavior. I stated the end behavior. Okay, this will always be the end behavior for odd degree power functions, for polynomial functions. If it's an even degree polynomial function, these two, of course, always stay the same. And then what would the blanks be? It'd be infinity, and this would be positive infinity as well. So notice the end behavior is different for odd degree and even degree power functions. So, okay, we answered that one well. Let's move on to a definition, a turning point. So that's a vocabulary word with these polynomial functions. So what do we mean by turning point? Just putting the cap on my pen here. A turning point on a graph. This is for a polynomial function, part of the personality, because rational functions, we don't talk about turning points. A turning point on a graph is a point where the function turns from increasing to decreasing or from decreasing to increasing. So here's an example with this graph here, which I just made up. Notice, you read a graph left to right. Isn't the graph going up here? It's increasing. And then all of a sudden it's going down or decreasing right at that precipice. That's going to be a turning point because it's going from increasing to decreasing. So that's a turning point. And then here's another turning point because here it's going, the graph is decreasing and now it's increasing, and right at that precipice, draw another point for another turning point. So this graph has two turning points. Here's a theorem now involving turning points. A theorem is a statement which can be proven, or you can just call it a fact. And this is an interesting theorem. It doesn't tell you a wealth of information, but it tells you some information. The number of turning points on the graph of a polynomial function of degree, let's call it the variable n, where n is any whole number, is at most n minus 1. So the number of turning points on the graph of a polynomial function of degree n is at most n minus 1. Let me give an example of this to make sure we understand that. Say we're given this polynomial function, f of x equals 7x to the 6 minus 3x squared plus 2. How many turning points are going to be there at most? We don't know exactly how many, but we know at most how many they're going to be. What's the degree of this polynomial function? So you got the term with the highest exponent, and that will be the degree for the whole function. So isn't the degree 6? Or in other words, n is 6 in our example right here. So how many at most turning points are there going to be? What's 6 minus 1? 5. So at most there'll be 5 turning points for that polynomial function. It has at most 5 turning points. What does that mean? That graph could have then either 5 turning points or 4 or 3 or 2 or 1 or 0 turning points. And now let's put a lot of things together with just this example. A true-false question. True or false, given this function, which does appear to be smooth and continuous, so it could represent a polynomial function. This graph could be this polynomial function. True or false? And I'll let you think about that for a moment. Notice that third term looks a little weird. Isn't that the same thing as this third term minus 1/2 x squared? Yeah, these two are exactly the same thing. So it's nice to know that. So, could this polynomial function give this graph? Well, how are we going to find out? How are we going to figure that out? Let's think about these three ideas that we are familiar with now. Let's think about end behavior. Let's think about the number of turning points. And what's the other one we want to think about? Well, it'll come to me later. So, what's the power function for here? Y equals 4x to the fifth. I'll write that down. Y equals 4x to the fifth is the power function. And isn't that of odd degree? So what do we know about the end behavior if it's an odd degree power function for your polynomial function? The ends go in opposite directions through the first and third quadrants, since this coefficient is positive. And let's look at this graph. Does this graph go through the first and third quadrants? First and third, for the ends of the graph. Did they go through the first and third quadrants? Yes. So far, it is a contender. It could be. How many, at most, how many turning points for this polynomial function? Isn't it going to be 5 minus 1 or 4? So at most, 4 turning points. Does this graph have either 4, 3, 2, 1, or 0 turning points? Yes. Doesn't it have 2 turning points? One there and one there. So it's still a contender. And then what is the other item? I know there was another one. Oh my, I'm going to look at my notes because I think it's in there. Just killing some time here. Let's see if I can get this. Let's see. I will. I see it now. Let me see. The degree. Oh, the degree is similar to power function. Yeah. So what's the degree of this function? Isn't the degree 5? So, yeah, that means at most there's going to be 4 turning points. So, the answer then is true. True. I'll circle it here. True. All right. It's been a dozen minutes, so I'll see you next time.